Hi, my name's Susanna, and I'm going to be solving a problem for ME304 with Professor Lehman that I'm taking during the summer 2020. So the problem states, shaft ABC is made of a solid section AB of A36 steel and a tubular section BC made of A36 steel, rigidly bonded, this is important, rigidly bonded, not use a highlighter. Actually, I'm gonna section this. AB is A36 steel, and then BC is also made of A36 steel, rigidly bonded to the core of 2014 T6 aluminum, and the applied torque at C has a magnitude of 50 feet, which we can see here. We can determine if it's positive or negative based on the direction. We'll get to that later. And the applied torque at B has a magnitude of 75 feet. Again, we will determine the direction and the sign later. Lengths and radius of each section as shown. Find the twist angle of C relative to the fixed end. So that will end up being the total twist angle from A to B and B to C. We're going to use a torque diagram to find that, just because these both might give different twist angles. So we need to add them together to get the twist angle relative to C. And then B, the maximum shear stress in the aluminum, we're only going to use section BC for that, and then the maximum shear stress in steel, so we're going to have to compare the maximum shear stress in both of them and see which one gives us a higher shear stress. Okay, so we're going to start off by writing our givens. Just makes it easier to come back to later. So for segment AB, we are going to have 836 steel. For this problem, we only need to know G, the modulus of rigidity. Which in this case, G of steel is equal to 11.2 times 10 to the 6 PSI. We can keep this in PSIs during our calculations. We don't need to change that or add or subtract anything. Our length from A to B is equal to 3 feet. And then our radius, which is our radius of steel at A to B, is very important, is equal to 1 inch. As we are given in this diagram, the radius is 1 inch throughout. All right, and then segment BC, we have both A36 and the 2014 aluminum, so we're going to do each part separately. 836 steel, same thing, the modulus of rigidity is the same, 11.2 times 10 to the 6 psi. The length of steel at BC is equal to 2 feet. The radius of steel is still equal to 1 inch. This is also the outer radius of segment BC. And then we have the 2014 T6 aluminum. Modulus of rigidity for aluminum is 3.9 times 10 to the 6 psi. The length is the same as the length of steel, so I'm just gonna make that little statement here. 2 feet. Radius of aluminum is 0.5 inches. We are given that in this diagram. And the radius of aluminum is also the inner radius, so just point that out. 0.5 inches. This is also, I'll just leave that. Okay, so we also need to plan. Because this is a statically indeterminate torque problem, because we need to solve for A, we also need to find the different torques in section B for aluminum and steel, and we just have more knowns than we have givens in this specific problem, so we need to follow a set of steps. So the first step, we're going to have to use an equilibrium equation. Right, step 2, we we need to use a torque diagram, which will give us our internal torques. Three, we need to use compatibility. Four, I feel like I'm missing something. Compatibility. I'm sorry, let me go check something. I think it's just calculate stresses, but I think I'm missing a step. Calculate stresses. Let me double check, just 1 second. That's probably fine. That's it. Okay. So can you see this? Okay. Yeah. Okay. Okay, so for one equilibrium, this is a summation of all of these torques. The magnitude of TB is equal to 75 pounds per feet. And now we need to find this torque. We don't know its direction or the magnitude yet, so that's what we're going to use equilibrium to find. So we're going to find torque A, also the regular torque A, not the magnitude. So we have, let's label these torque C and torque B. So we have torque A plus torque B plus torque C is equal to 0. Okay. For A, this is what we were looking for. For B, we notice that it's going counterclockwise, so it's actually going to be positive. And then for torque C, the torque is going in the clockwise direction, so it's going to be negative. 0, torque A is equal to 25, negative 25, right? And so now we can go on to step 2. Well, we know all of our torques. This gives us torque A is negative 25, so that the magnitude of torque A is equal to 25, and it's in the negative direction, so it's clockwise. So this is going to go like this. Oh, it's not writing like that. Torque A is equal to 25 pounds per feet. Per pounds of feet here. Keep our units. Right, and now we go on to our torque diagram. Okay. For our torque diagram, we need to keep in mind which is our x direction. So since this is a fixed end, we can point our x axis this way, and therefore we will draw our x diagram, torque diagram like this, with the x pointing the same direction as our initial diagram. And starting from the origin, we have A, 3 feet later we have B, and then 2 feet later we have C. Okay, so, and then going into our torque diagram, we have to remember that the internal torque is going to be the opposite direction of our normal torque. So TA is going counterclockwise, and that's negative. Our torque diagram is going to give us a positive 25. Torque pounds per feet is just x. Right, and then all the way to B, there's going to be no reaction until it hits B, and at B it's going to go counterclockwise 75 pounds per feet. So the opposite of that would be negative 75, so we go down 25, and then we go down 50 to make the one. This is negative 50, and then continuing on to C. C is going to make a reaction of 50 pounds per feet in the positive direction because it's going clockwise, and then it should go back to 0 like that. Just like to fill this in to give a clear look. This is positive. This is negative. Here we go. So this is our internal torque. I just like to note that. So we have from A to B, torque from A to B will give us 25 pounds per feet. And then torque of BC is equal to negative 50 pounds per V. So from this we can tell torque of AB, the internal torque is going to be positive, so it's actually going to be turning clockwise. So this is going to be going this way, while torque of BC is going that way. So it's going to look something like this, but this one's going to be turning, this should go more than this one. So our final twist angle should actually be negative, since this one is being able to turn more than torque of AB. Right? So going to our compatibility, we can also note that T of BC, while it is equal to negative 50, it is also equal to the torque of aluminum plus the torque of steel only at BC. The torque of steel from A to B is different from the torque of steel to BC, so keep that in mind. Just gonna put a little star. Right, and we also know, since, let's just note this, since aluminum and steel are rigidly bonded at BC, the twist angle, the twist angle of the steel, just gonna put it at BC. BC is equal to the twist angle of aluminum at BC. Okay? And we're going to use this equation, the twist angle equation, to find our torque of aluminum and our torque of steel. So this is going to be equation 1, and this is going to be equation 2. Look up here. Okay? We also have our twist angle is equal to TL over JG. T is equal to torque, L is our length, G is our polar moment of inertia. Yeah, polar moment of inertia. Before I go on to G, I'm also going to note that the polar moment of inertia for a solid sphere is different than the polar moment of inertia for a hollow cylinder. So for a solid cylinder, J is equal to pi over 2 R4, and then J for a hollow cylinder, J is equal to pi over 2, and keep this in mind, this is our outer to the power 4 minus our inner to the power 4. This will make a huge difference when doing calculations, so it's very important not to mix these up. And then our J, we already went over this. This is our modulus of rigidity, whatever, you know what I mean, rigidity. Okay, so here we have the twist angle of steel, right? Steel is equal to T of steel, L of steel over J of steel and G of steel. We also have twist angle of aluminum is equal to T of aluminum, L of aluminum, J of aluminum, and G of aluminum. We can also note we can substitute one of these equations in here, one of these already, just for simplicity terms. So I'm going to be using negative 50 is equal to T of aluminum plus T of steel. I'm going to be solving for T of aluminum. T of aluminum is equal to negative 50 minus T of steel. And that's what we're going to plug in over here. So just going to do here. Right, and we're going to set these equal to each other, because as we already noted, they should be equal to each other in section BC. Only in section B of C. That's the only one aluminum isn't anyway, so we have T of steel is equal to L of steel, J of steel, G of steel is equal to plugging this in, we have negative 50 minus T of steel, L of aluminum, J of aluminum, and G of aluminum. Already we can cancel out T of steel and T of aluminum because, as we pointed out before, T of steel is equal to T of aluminum for section B of segment BC, which is equal to 2 feet. So they would cancel out anyways. Just gonna leave the problem there. All right. Okay, now we can just plug in our variables and everything. T of steel is equal to, we never solved for J's. Let me do our J's. So J of steel is equal to pi over 2. Steel in segment B of C, as we noted, is hollow, so it is going to take this equation. So pi over 2, our outer, is 1 then to the power of 4 minus 0.5 to the power of 4, right? I'm going to leave it like that just so we don't have to calculate it right now. G of aluminum is equal to pi over 2. Aluminum is a solid cylinder, so we use this polar moment of inertia, r to the 4, which is just 0.5 to the 4. It's pretty easy. Okay, gonna leave that up here and use this one. Can you see that? Both of them? So, there you go. Okay, so now we're gonna plug in our variables. T of steel over J of steel, which is pi over 2, 1 to the power of 4 minus 0.5 to the power of 4. These are going to be inches. I'm just going to leave inches here off to the side. And then our G of steel, as is pointed here. Can you see that? Our G of steel is 11.2 times 10 to the 6 psi. We already cancel our L, so that's why there's no L here. And then this is negative 50 minus T of steel over J, which is pi over 2. We have this here, the aluminum, 0.5 to the power of 4, and then G, 3.9 times 10 to the 6 times 10 to the 6 psi. Okay? So already we can cancel the pi over 2 as well out. There you go. And then going into our calculations, I did this part of calculations ahead of time just so it's a little bit easier. We don't have to spend too much time on that part. So we get 9.52381 times 10 to the negative 8 T of steel. That is what this value is equal to. And then I did T of steel over this and then 50 over this, so we have negative 4.10256 times 10 to the negative 6 T of steel minus 2.0513 times 10 to the negative 4. There you go. And then we move this over, so we add this to both sides. We get 4.1978 times 10 to the 6, 10 to the negative 6 T of steel is equal to, again, nothing changed on this side, on this to this value, negative 2.0513 times 10 to the negative 4. Okay. Right, and then dividing from both sides, we get T of steel is equal to negative 48.86552 pounds feet. All right, and that makes sense. T of steel should be greater than our T of aluminum. It's bigger, has more area, volume in general, and it is stronger than the aluminum regardless, so it should have a higher torque value. All right, higher absolute torque value, of course. And then we also, going back to this equation we have here, again, negative 50 is equal to T of aluminum plus T of steel. Negative 50 is equal to T aluminum minus 48.86562. I just keep a lot of decimals just for accuracy purposes. Adding this to both sides, it gives us T of aluminum is equal to 1.1343 pounds-feet. So this is important. I'm gonna highlight it. Highlight that. Highlight that. All right. Okay. So now we can go on to our twist angles. So we know that our twist angle from A to C will give us our twist angle of C, right? So relative to the fixed point at C, we're gonna have the twist angle from A to B, which should give us a positive value subtracted from the twist angle from B to C, so it's gonna be a negative value. So our final answer, our twist angle from A to C, which is a twist angle from C, but I'm gonna leave it as A to C for just to understand it better. It should be negative, so predict should be negative. Predict should be negative. Okay, I stand by that. Okay, and we also know that our twist angle from A to B should be the sum of twist angles, so I'm gonna write that down in equation terms. So our twist angle from A to C is our twist angle from A to B plus our twist angle from B to C. Okay. Okay, so easy. We're gonna do the first part. Twist angle from A to B is equal to. We already know this is gonna be TL over JG, and since from A to B it's only steel, it's pretty easy. The torque of steel from A to B is 25. Right. The length from A to B is, okay, actually let me keep my units to not mess up. So it's 25 pounds per feet, but we want to keep this in inches, so we're going to multiply this by 12 inches by feet. Feet cancel out. Same thing, the length is going to be 3 feet. Here we go, we wrote it down here, 3 feet. Again, times 12 inches over 1 foot. There you go. Over our J, which we already, oh, we actually didn't do our J for AB. Anyways, it's gonna be pi over 2. For the segment, it's a solid cylinder, so our R is gonna be 1, R4, and then our G is going to be 11.2 times 10 to the 6 PSI. Sorry, this is inches for. There you go. Solving our angle from A to B. From A to B, it should give us 6.1388 times 10 to the negative 4 radians. You can either keep this in radians or solve in degrees. I just do the degrees at the end just for simplicity terms. And then we're gonna go to here of BC. Now we already know that the twist angle from B to C could be either the twist angle from aluminum or the twist angle from steel from B to C. So we can do either one. So let's do this to steel, right? So actually I'm gonna go over both of them to make sure that they're the same. If they're not the same, then it probably means I did something wrong. So just to check, I'm gonna do both of them and make sure they equal each other. Aluminum, we know that, so the T of aluminum is here. Oh, sorry, this is negative. Yeah. This is 1.1343. TL, the L from aluminum is 2. I'm sorry, I'm gonna make this simpler. TL over JG. There you go. So this is equal to negative 1.1343, right? Pounds feet. And multiply it by 12 inches per feet. Okay. From aluminum, this is BC. At BC, this is equal to 2 feet. again times 12 feet, 12 inches over 1 foot. Feet cancel out, over J. J of AL, we already did that work here. Pi over 2, 0.54. And then the G of aluminum was 3.9 times 10 to the 6 psi. Sorry, I forgot inches again here. There you go. And then calculating this, I already calculated it ahead of time, is equal to negative 8.5321 times 10 to the negative 4. Right? And then, so we're going to check our steel, make sure they're the same. If they're the same, we can continue. TL over JG is equal to negative 48.86562 pounds feet times 12 inches feet. Feet cancel out. Times 2 feet times 12 inches over 1 foot. There you go, those cancel out. J, we did it again here, because this is from segment BC. Right, pi over 2, 1/4 minus 0.5 to the power of 4 inches. G is 11.2 times 10 to the 6 psi. Okay, calculating that. We have the twist angle of steel from B to C is equal to negative 8.5327 times 10 to the negative 4. It's radians, radians. As you can see, these are fairly similar. They only differ from the 1, 2, 3, from the 4th decimal point. So, and even then it's to the negative 4, so that's like to the 8th decimal point in reality. So they're almost the exact same value. Probably could have been a rounding error why they're not exact, but we can say that the twist angle from aluminum and the twist angle of steel are the same. Right. Okay, now moving on to this next part, solving for, we can use either one. I'm going to use aluminum, BC. Right, we already solved for it, negative 8.5321 times 10 to the negative 4 radians, right? And then our twist angle from A to C is equal to twist angle A to B plus twist angle of BC. Okay, this is equal to, what do we get for the first one? For the first one we got, I'm gonna highlight this. 6.1388 times 10 to the negative 4 plus negative 8.5321 times 10 to the negative 4. This is in radians. Twist angle from A to B, already calculated ahead of time. It's going to be negative 2.3939 times 10 to the negative 4 radians. Okay. We can simplify that. I'm just going to convert it into degrees just because I can. I guess. Just 1 second. I'm just going to punch it in. 39. So to convert it to radians to degrees, it's 188 degrees over pi radians. The radians cancel out. Sigma A to B is equal to 180 over pi. 0.0137 degrees. Okay, so this is our answer. I'm gonna keep both of them because it doesn't matter, they're the same. It's negative 4 radians. They're both right, they're both the same thing. Alright, this is our answer for section for A. Here we go. There you go. Alright, and now moving on to part B. Okay, so we already did our equilibrium, our torque diagrams, and our compatibility. Sorry, I didn't explain the steps while I was doing them. They're pretty easy to differentiate between steps, so I don't think that should be a problem. Moving on to our last step, we're going to calculate our stresses. Here, calculate stresses. Okay, so we're calculating our shear stress in aluminum and our shear stress in steel. Okay, so we have our tau of aluminum is equal to TC over J. Haven't gone over C. C is the distance from the center. Distance from center to the outermost fiber. Okay, so it's basically the radius to the outer edge of whatever material we're using. Okay, so T of aluminum is equal to the T of aluminum. It's only from B to C. We already did T. We said it was negative 1.1343 pounds feet. Okay, and our C from aluminum to the outermost fiber of aluminum is 0.5. So 0.5 inches. Okay, and we're going to multiply this by 12 inches per feet to cancel these feet out. And then our J, as we already said previously, is pi over 2 r to the power of 4, which is 0.5 to the power of 4. Okay, this comes out to negative 69.32 KSI. In this case, the sign of the maximum shear stress can be relative. We don't really need it in our answer from what I'm told in class. I'm going to leave the negative there, just it's easier to understand for me. Okay, and then since we have two stresses for steel, we have to calculate both of the stresses and decide which one is the max stress. So I'm going to do A to B first. So from steel, TC over J. Okay, T of steel from A to B is 25. We already got that from our torque diagram. I don't think I need to go back, but I will still show it. Where did it go? Oh, here it is. Remember, we got 25 for A to B, and that is T of steel from A to B. T of steel, pounds per feet, 12 inches per feet. And then our C for steel from A to B is just equal to 1 because the outermost fiber is the radius. It's 1 inch. And then it's pi over 2, and it's because A to B is solid, not hollow. It's just pi over 2 r to the 4th. R is, we already said, is 1 inch to the 4. Okay. And then, so this T of steel will give us, I think it's 190.986 KSI. Okay, and then we're going to compare it to the shear stress from B to C of the steel. Steel, TC over J. We already found this out going back to our highlighted area. There you go. Negative 48.86562 pounds feet times 12 inches, 1 foot. And then our C is still the outermost fiber, which is still 1 inch. That does not change. And then our J is going to be different because in this case this was hollow, whereas A to B was solid. So pi over 2, here we have 1 to the power of 4, that's our outer radius, minus our inner radius, which is 0.5 to the power of 4. Okay, this will give us the shear stress of steel from B to C, which is equal to negative 9398.193 KSI. Okay, so even though this is positive and this is negative, that does not mean that this is the maximum shear stress, because we're actually looking at the absolute maximum shear stress. So T max of aluminum, I guess I should write tau of aluminum max. I'm gonna write absolute values, is equal to 69.32 KSI. And since we're looking at the absolute value, the signs do not matter, like I already said. So we're gonna take, this is our largest, this is our maximum shear stress here. So our T of steel maximum absolute value, it's equal to 398.193 KSI. And there we have it. This is B, and this is C. Just gonna box that. Okay, and just a quick review of everything we did to like really grasp everything. I'm gonna go back to the beginning. So, starting off, we read the problem, we got our givens, we took down all of our givens so that we didn't have to come back to the main problem to take that from it. Okay, we did our equilibrium equations. From our equilibrium equations, sorry, it's all mixed up now. From our equilibrium equations, we found that T of A is equal to negative 25 pounds per feet, keeping in mind that it went in a clockwise direction. The clockwise direction gave us a positive starting torque of 25. So from T to the torque from A to B is 25, and then we also found that our torque from B to C is negative 50 based on our torque diagram, right? And then using our compatibility equations, twist angle from steel from B to C and our twist angle from aluminum B to C, we found our T of steel and T of aluminum to come out to this should be equal to negative 50, which it was. Oh yeah, we also predicted that our angle was going to come out to a negative angle, and going back to that, it was negative, so we can assume that we are probably right. And then we have our shear stresses down here after we calculated all our stresses. And yeah, that is all. Those are all the steps in the summation. And that's it. Just gonna show my face, I guess, but oh. Actually, gotta sign it. That's my signature. Whatever. And that's it.